Chapter 1, Part 1 of A Popular History of Astronomy during the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy during the 19th Century by Agnes Mary Clerke. Part 1, Progress of Astronomy during the First Half of the 19th Century. Chapter 1, Foundation of Sidereal Astronomy, Part 1. Until nearly 100 years ago, the stars were regarded by practical astronomers mainly as a number of convenient fixed points by which the motions of the various members of the solar system could be determined and compared. Their recognized function, in fact, was that of milestones on the great celestial highway traversed by the planets, as well as on the byways of space, occasionally pursued by comets. Not that curiosity as to their nature and even conjecture as to their origin were at any period absent. Both were from time to time powerfully stimulated by the appearance of startling novelties in a region described by philosophers as incorruptible or exempt from change. The catalogue of Hipparchus probably, and certainly that of Tycho Brahe some 17 centuries later, owed each its origin to the temporary blaze of a new star. The general aspect of the skies was thus, however imperfectly, recorded from age to age, and with improved appliances the enumeration was rendered more and more accurate and complete, but the secrets of the stellar sphere remained inviolate. In a qualified, though very real sense, Sir William Herschel may be called the founder of sidereal astronomy. Before his time some curious facts had been noted and some ingenious speculations hazarded regarding the condition of the stars, but not even the rudiments of systematic knowledge had been acquired. The facts ascertained can be summed up in a very few sentences. Giordano Bruno was the first to set the suns of space in motion, but in imagination only. His daring surmise was, however, confirmed in 1718, when Halley announced that Sirius, Aldebaran, Betelgeuse, and Arcturus had unmistakably shifted their quarters in the sky since Ptolemy assigned their places in his catalogue. A similar conclusion was reached by J. Cassini in 1738 from a comparison of his own observations with those made at Cayenne by Richet in 1672. And Tobias Mayer drew up in 1756 a list showing the direction and amount of about 57 proper motions, founded on star places determined by Olaus Römer 50 years previously. Thus the stars were no longer regarded as fixed, but the question remained whether the movements perceived were real or only apparent, and this it was not yet found possible to answer. Already in the previous century the ingenious Robert Hooke had suggested an alteration of the very system of the sun to account for certain suspected changes in stellar positions. Bradley in 1748 and Lambert in 1761 pointed out that such apparent displacements, by that time well ascertained, were in all probability a combined effect of motions both of sun and stars, and Mayer actually attempted the analysis, but without result. On the 13th of August, 1596, David Fabricius, an unprofessional astronomer in East Friesland, saw in the neck of the Whale a star of the third magnitude, which by October had disappeared. It was nevertheless visible in 1603, when Bayer marked it in his catalogue with the Greek letter omega, and was watched in 1638-39 through its phases of brightening and apparent extinction by a Dutch professor named Hulwarda. From Hevelius, this first known periodical star, received the name of Mira, or the Wonderful, and Boulliud in 1667 fixed the length of its cycle of change at 334 days. It was not a solitary instance. A star in the Swan was perceived by Janssen in 1600 to show fluctuations of light, and Montanari found in 1669 that Algol in Perseus shared the same peculiarity to a marked degree. Altogether, the class embraced in 1782 half a dozen members. When it is added that a few star couples had been noted in singularly, but it was supposed accidentally, close juxtaposition, and that the failure of repeated attempts to measure stellar parallaxes pointed to distances at least 400,000 times that of the earth from the sun, the picture of sidereal science, when the last quarter of the 18th century began, is practically complete. It included 3 items of information: that the stars have motions, real or apparent; that they are immeasurably remote; and that a few shine with a periodically variable light. Nor were these scantily collected facts ordered into any promise of further development. They lay at once isolated and confused before the inquirer. They needed to be both multiplied and marshalled, and it seemed as if centuries of patient toil must elapse before any reliable conclusions could be derived from them. The sidereal world was thus the recognized domain of far-reaching speculations, which remained wholly uncramped by systematic research until Herschel entered upon his career as an observer of the heavens. The greatest of modern astronomers was born at Hanover, November 15, 1738. He was the 4th child of Isaac Herschel, a hautboy player in the band of the Hanoverian Guard, and was early trained to follow his father's profession. On the termination, however, of the disastrous campaign of 1757, his parents removed him from the regiment, there is reason to believe, in a somewhat unceremonious manner. Technically, indeed, he incurred the penalties of desertion, remitted, according to the Duke of Sussex's statement to Sir George Airy, by a formal pardon handed to him personally by George III. On his presentation in 1782. At the age of 19, then, his military service having lasted 4 years, he came to England to seek his fortune. Of the life of struggle and privation which ensued, little is known beyond the circumstances that in 1760 he was engaged in training the regimental band of the Durham militia, and that in 1765 he was appointed organist at Halifax. In the following year he removed to Bath as oboist in Linley's orchestra, and in October 1767 was promoted to the post of organist in the Octagon Chapel. The tide of prosperity now began to flow for him. The most brilliant and modish society in England was at that time to be met at Bath, and the young Hanoverian quickly found himself a favourite and the fashion in it. Engagements multiplied upon him. He became director of the public concerts. He conducted oratorios, engaged singers, organized rehearsals, composed anthems, chants, choral services, besides undertaking private tuitions, at times amounting to 35 or even 38 lessons a week. He, in fact, personified the musical activity of a place then eminently and energetically musical. But these multifarious avocations did not take up the whole of his thoughts. His education, notwithstanding the poverty of his family, had not been neglected, and he had always greedily assimilated every kind of knowledge that came in his way. Now that he was a busy and a prosperous man, it might have been expected that he would run on in the deep professional groove laid down for him. On the contrary, his passion for learning seemed to increase with the diminution of the time available for its gratification. He studied Italian, Greek, mathematics. Maclaurin's fluxions served to unbend his mind. Smith's harmonics and optics and Ferguson's astronomy were the nightly companions of his pillow. What he read stimulated without satisfying his intellect. He desired not only to know, but to discover. In 1772 he hired a small telescope, and through it caught a preliminary glimpse of the rich and varied fields in which for so many years he was to expatiate. Henceforward the purpose of his life was fixed. It was to obtain a knowledge of the construction of the heavens, and this sublime ambition he cherished to the end. A more powerful instrument was the first desideratum, and here his mechanical genius came to his aid. Having purchased the apparatus of a Quaker optician, he set about the manufacture of specula with a zeal which seemed to anticipate the wonders they were to disclose to him. It was not until 15 years later that his grinding and polishing machines were invented, so the work had at that time to be entirely done by hand. During this tedious and laborious process, which could not be interrupted without injury, and lasted on one occasion 16 hours, his strength was supported by morsels of food put into his mouth by his sister, and his mind amused by her reading aloud to him the Arabian Nights, Don Quixote, or other light works. At length, after repeated failures, he found himself provided with a reflecting telescope, a 5½ foot Gregorian of his own construction. A copy of his first observation with it on the great nebula in Orion, an object of continual amazement and assiduous inquiry to him, is preserved by the Royal Society. It bears the date March 4, 1774. In the following year he executed his first review of the heavens, memorable chiefly as an evidence of the grand and novel conceptions which already inspired him, and of the enthusiasm with which he delivered himself up to their guidance. Overwhelmed with professional engagements, he still contrived to snatch some moments for the stars, and between the acts at the theatre was often seen running from the harpsichord to his telescope, no doubt with that uncommon precipitancy which accompanied all his actions. He now rapidly increased the power and perfection of his telescopes. Mirrors of 7, 10, even 20 feet focal length were successively completed, and unprecedented magnifying powers were employed. His energy was unceasing, his perseverance indomitable. In the course of 21 years, no less than 430 parabolic specula left his hands. He had entered upon his 42nd year when he sent his first paper to the Philosophical Transactions. Yet during the ensuing 39 years his contributions, many of them elaborate treatises, numbered 69, forming a series of extraordinary importance to the history of astronomy. As a mere explorer of the heavens, his labours were prodigious. He discovered 2,500 nebulae, 806 double stars, passed the whole firmament in review for several times, counted the stars in 3,400 gauge fields, and executed a photometric classification of the principal stars, founded on an elaborate and the first systematically conducted investigation of their relative brightness. He was as careful and patient as he was rapid, spared no time and omitted no precaution to secure accuracy in his observations. Yet in one night he would examine singly and attentively up to 400 separate objects. The discovery of Uranus was a mere incident of the scheme he had marked out for himself, a fruit gathered, as it were, by the way. It formed, nevertheless, the turning point in his career. From a star-gazing musician he was at once transformed into an eminent astronomer. He was relieved from the drudgery of a toilsome profession and installed as royal astronomer, with a modest salary of £200 a year. Funds were provided for the construction of the 40-foot reflector, from the great space-penetrating power of which he expected unheard-of revelations. In fine, his future work was not only rendered possible, but it was stamped as authoritative. On Whit Sunday, 1782, William and Caroline Herschel played and sang in public for the last time in St. Margaret's Chapel, Bath. In August of the same year the household was moved to Datchet, near Windsor, and on April 3, 1786, to Slough. Here happiness and honours crowded on the fortunate discoverer. In 1788 he married Mary, only child of James Baldwin, a merchant of the city of London, and widow of Mr. John Pitt, a lady whose domestic virtues were enhanced by the possession of a large jointure. The fruit of their union was one son, of whose work, the worthy sequel of his father's, we shall have to speak further on. Herschel was created a knight of the Hanoverian Guelphic order in 1816, and in 1821 he became the first president of the Royal Astronomical Society, his son being its first foreign secretary. But his health had now for some years been failing, and on August 25, 1822, he died at Slough in the 84th year of his age, and was buried in Upton churchyard. His epitaph claims for him the lofty praise of having burst the barriers of heaven. Let us see in what sense this is true. The first to form any definite idea as to the constitution of the stellar system was Thomas Wright, the son of a carpenter living at Byers Green, near Durham. With him originated what has been called the grindstone theory of the universe, which regarded the Milky Way as the projection on the sphere of a stratum or disk of stars, our sun occupying a position near the centre, similar in magnitude and distribution to the lucid orbs of the constellations. He was followed by Kant, who transcended the views of his predecessor by assigning to nebulae the position they long continued to occupy, rather on imaginative than scientific grounds, of island universes, external to and coequal with the galaxy. Johann Heinrich Lambert, a tailor's apprentice from Mulhausen, followed, but independently. The conceptions of this remarkable man were grandiose, his intuitions bold, his views on some points a singular anticipation of subsequent discoveries. The sidereal world presented itself to him as a hierarchy of systems, starting from the planetary scheme, rising to throngs of suns within the circuit of the Milky Way, the ecliptic of the stars, as he phrased it, expanding to include groups of many Milky Ways, these again combining to form the unit of a higher order of assemblage, and so onwards and upwards until the mind reels and sinks before the immensity of the contemplated creations. Thus everything revolves: the earth round the sun round the centre of his system, this system round a centre common to it with other systems, this group, this assemblage of systems round a centre which is common to it, with other groups of the same kind, and where shall we have done? The stupendous problem thus speculatively attempted, Herschel undertook to grapple with experimentally. The upshot of this memorable inquiry was the inclusion, for the first time within the sphere of human knowledge, of a connected body of facts, and inferences from facts, regarding the sidereal universe; in other words, the foundation of what may properly be called a science of the stars. Tobias Mayer had illustrated the perspective effects which must ensue in the stellar sphere from a translation of the solar system, by comparing them to the separating in front and closing up behind of trees in a forest to the eye of an advancing spectator; but the appearances which he thus correctly described he was unable to detect. By a more searching analysis of a smaller collection of proper motions, Herschel succeeded in rendering apparent the very consequences foreseen by Mayer. He showed, for example, that Arcturus and Vega did in fact appear to recede from, and Sirius and Aldebaran to approach each other by very minute amounts, and with a striking effort of divinatory genius placed the apex or point of direction of the sun's motion close to the star Lambda in the constellation Hercules, within a few degrees of the spot indicated by later and indefinitely more refined methods of research. He resumed the subject in 1805, but though employing a more rigorous method, was scarcely so happy in his result. In 1806 he made a preliminary attempt to ascertain the speed of the sun's journey, fixing it by doubtless much too low an estimate at about 3 miles a second. Yet the validity of his general conclusion as to the line of solar travel, though long doubted, has been triumphantly confirmed. The question as to the secular parallax of the fixed stars was in effect answered. With their annual parallax, however, the case was very different. The search for it had already led Bradley to the important discoveries of the aberration of light and the nutation of the earth's axis. It was now about to lead Herschel to a discovery of a different, but even more elevated character. Yet in neither case was the object primarily sought attained. From the very first promulgation of the Copernican theory, the seeming immobility of the stars had been urged as an argument against its truth, for if the earth really travelled in a vast orbit round the sun, objects in surrounding space should appear to change their positions, unless their distances were on a scale which, to the narrow ideas of the universe then prevailing, seemed altogether extravagant. The existence of such apparent or parallactic displacements was accordingly regarded as the touchstone of the new views, and their detection became an object of earnest desire to those interested in maintaining them. Copernicus himself made the attempt, but with his triquetrum, a jointed wooden rule with the divisions marked in ink, constructed by himself, he was hardly able to measure angles of 10 minutes, far less fractions of a second. Galileo, a more impassioned defender of the system, strained his ears, as it were, from Arcetri, in his blind and sorrowful old age, for news of a discovery which 2 more centuries had still to wait for. Hooke believed he had found a parallax for the bright star in the head of the Dragon, but was deceived. Bradley convinced himself that such effects were too minute for his instruments to measure. Herschel made a fresh attempt by a practically untried method. It is a matter of daily experience that 2 objects situated at different distances seem to a beholder in motion to move relatively to each other. This principle Galileo, in the third of his dialogues on the systems of the world, proposed to employ for the determination of stellar parallax. For 2 stars lying apparently close together, but in reality separated by a great gulf of space, must shift their mutual positions when observed from opposite points of the earth's orbit, or rather the remoter forms a virtually fixed point to which the movements of the other can be conveniently referred. By this means complications were abolished, more numerous and perplexing than Galileo himself was aware of, and the problem was reduced to one of simple micrometrical measurement. The double star method was also suggested by James Gregory in 1675, and again by Wallace in 1693. Huggins first, and afterwards Dr. Long of Cambridge, about 1750, made futile experiments with it, and it eventually led, in the hands of Bessel, to the successful determination of the parallax of 61 Cygni. Its advantages were not lost upon Herschel. His attempt to assign definite distances to the nearest stars was no isolated effort, but part of the settled plan upon which his observations were conducted. He proposed to sound the heavens, and the first requisite was a knowledge of the length of his sounding line. Thus it came about that his special attention was early directed to double stars. "I resolved," he writes, "to examine every star in the heavens with the utmost attention and a very high power, that I might collect such materials for this research as would enable me to fix my observations upon those that would best answer my end. The subject has already proved so extensive, and still promises so rich a harvest to those who are inclined to be diligent in the pursuit, that I cannot help inviting every lover of astronomy to join with me in observations that must inevitably lead to new discoveries." The first result of these inquiries was a classed catalogue of 269 double stars, presented to the Royal Society in 1782, followed, after 3 years, by an additional list of 434. In both these collections the distances separating the individuals of each pair were carefully measured, and with a few exceptions the angles made with the hour circle by the lines joining their centres, technically called angles of position, were determined with the aid of a revolving wire micrometer specially devised for the purpose. Moreover, an important novelty was introduced by the observation of the various colours visible in the star couples, the singular and vivid contrasts of which were now for the first time described. Double stars were at that time supposed to be a purely optical phenomenon. Their components, it was thought, while in reality indefinitely remote from each other, were brought into fortuitous contiguity by the chance of lying nearly in the same line of sight from the earth. Yet Bradley had noticed a change of 30 degrees between 1718 and 1759 in the position angle of the two stars forming Castor, and was thus within a hair's breadth of the discovery of their physical connection. While the Reverend John Michell, arguing by the doctrine of probabilities, wrote as follows in 1767: "It is highly probable in particular, and next to a certainty in general, that such double stars as appear to consist of two or more stars placed very near together, do really consist of stars placed near together, and under the influence of some general law." And in 1784, "It is not improbable that a few years may inform us that some of the great number of double, triple stars, etc., which have been observed by Mr. Herschel, are systems of bodies revolving about each other." This remarkable speculative anticipation had a practical counterpart in Germany. Father Christian Mayer, a Jesuit astronomer at Mannheim, set himself in January 1776 to collect examples of stellar pairs, and shortly after published the supposed discovery of satellites to many of the principal stars. But his observations were neither exact nor prolonged enough to lead to useful results in such an inquiry. His disclosures were derided, his planet stars treated as results of hallucination. "On n'a point cru à des choses aussi extraordinaires," wrote Lalande, within 1 year of a better grounded announcement to the same effect. Herschel at first shared the general opinion as to the merely optical connection of double stars. Of this the purpose for which he made his collection is in itself sufficient evidence, since what may be called the differential method of parallaxes depends, as we have seen, for its efficacy upon disparity of distance. It was much too soon, he declared in 1782, to form any theories of small stars revolving round large ones, while in the year following he remarked that the identical proper motions of the two stars forming to the naked eye the single bright orb of Castor could only be explained as both equally due to the systematic parallax caused by the sun's movement in space, plainly showing that the notion of a physical tie compelling the two bodies to travel together, had not as yet entered into his speculations; but he was eminently open to conviction, and had, moreover, by observations unparalleled in amount as well as in kind, prepared ample materials for convincing himself and others. In 1802 he was able to announce the fact of his discovery, and in the 2 ensuing years to lay in detail before the Royal Society proofs, gathered from the labours of a quarter of a century, of orbital revolution in the case of as many as 50 double stars, henceforth he declared to be held as real binary combinations, intimately held together by the bond of mutual attraction. The fortunate preservation in Dr. Maskelyne's note-book of a remark made by Bradley about 1759 to the effect that the line joining the components of Castor was an exact prolongation of that joining Castor with Pollux, added 18 years to the time during which the pair were under scrutiny, and confirmed the evidence of change afforded by more recent observations. Approximate periods were fixed for many of the revolving suns: for Castor 342 years, for Gamma Leonis 1200, Delta Serpentis 375, Sigma Bootis 1681 years. Sigma Lyrae was noted as a double star, a change of relative situation having been detected in each of the two pairs composing the group, and the occultation was described of one star by another in the course of their mutual revolutions, as exemplified in 1795 by the rapidly circulating system of Zeta Hercules. Thus, by the sagacity and perseverance of a single observer, a firm basis was at last provided upon which to raise the edifice of sidereal science. The analogy long presumed to exist between the mighty star of our system and the bright points of light spangling the firmament was shown to be no fiction of the imagination, but a physical reality. The fundamental quality of attractive power was proved to be common to matter so far as the telescope was capable of exploring, and law, subordination, and regularity to give testimony of supreme and intelligent design, no less in those limitless regions of space than in our narrow terrestrial home. The discovery was emphatically, in Arago's phrase, one with a future, since it introduced the element of precise knowledge where more or less probable conjecture had previously held almost undivided sway, and precise knowledge tends to propagate itself and advance from point to point. End of Chapter 1, Part 1.